later on. Okay. So today we will start the first session of engineering principles, and we will cover understand applications of SI units and measurement. So in this session, we will be discuss the historical development of SI system, which is International System of Units. Then we create a comprehensive table for 22 derived units with special names and symbols. So this is used in SI system and demonstrate ability to use SI units in practical context. So the first one is the historical development of SI system. So the International System of Units, it is commonly known as SI, is the modern form of metric system and is widely used system of measurement worldwide. Its development has evolved over centuries. That means it has been used for quite a long time, from ancient units and finally resulting into standardization of SI units in the 20th century.
Yeah.
So the next one is the historical developments. We will cover the different phases such as ancient units, introduction to the metric system, decimal system, the adoption and spread, the International Bureau of Weights and Measures, which measures basically the gram, the kilogram units. Then we have development of SI, the evolving definitions, and modern advancements. So the first thing we look into the ancient units. So it can the evolution of SI system can be traced back to ancient civilizations such as Egyptians, the Greeks, who developed their own systems for measuring length, mass, and time. So these are the three most fundamental units. However, these were not consistent, and each of these civilizations, they followed their own units. So the precursor to the SI system was the metric system, which was developed during in the French Revolution. So a diverse collection of regional measurement systems were in use at that time. So the French Academy of Sciences, what they did is that they consolidated all of these measurement units to establish the first version of the metric system, which included units like the meter, the gram, and the liter. So these three are the most fundamental units of measurement with respect to the length, the weight, and again the quantity. So decimal system. So decimal system was one of the most evolved form of the metric system, and it was based on decimal multiples and submultiples. So this allowed conversion between units by simply shifting the decimal point, making calculations and measurements more straightforward. So the decimal system was one of the first stages of evolution of the SI unit. Then how did it spread across? So the metric system, it gained popularity across Europe during the 19th century, where it found use in various fields such as science, commerce, industry, engineering. So by the end of 19th century, many countries had already adopted the metric system, but slight variations in units already existed, as each of the countries, they used slightly different versions of the metric system. So in 1875, the Treaty of the Meter established the International Bureau of Weights and Measures in France. So this international body was tasked with preserving the international prototype kilogram and other reference standards. So it is still there in its museum today. It served as the international authority for ensuring uniformity in measurement. So basically, this can be used as a reference point for measuring the kilogram and its reference weight. Now we come to the development of SI. So the SI system, as we know it today, was established during the 20th century, which was not very far back. So in 1960, the 11th General Conference on Weights and Measures, they introduced the SI system, and which was formulated as an extension of the metric system. So it was based on 7 fundamental units, which included the meter for length, kilogram for mass, seconds for time, ampere for electric current, Kelvin for temperature, candela for luminous intensity, and mole for amount of substance. So these were the 7 fundamental units of the SI system. So as time progressed, there were further more evolution in the in the use of SI system, and to ensure greater precision and stability, the definitions of SI have been revised over time. For example, the meter was originally defined as 1/10 millionth of distance from North Pole to equator along the meridian passing through Paris. Today, it is defined as the distance that light travels in vacuum during 1 by 300 million, approximately 300 million seconds. So, the quest for further refining and bringing in precision in the measurement of the units is still in progress. And in modern advancements, we see that it has become very important to redefine certain units so that they provide more precision and more accuracy in measuring the 7 fundamental units of SI system. For example, the kilogram was redefined in 2019 based on Planck constant, ensuring a more stable and accurate standard. So there are advancements going on, but so that there is more greater accuracy in measuring the different fundamental parameters. So next we look into the comprehensive table for 22 derived units with special names and symbols. So we discussed, there are 7 fundamental units for measurement in the SI system. It is meter for length, kilogram for mass, seconds for time, ampere for electric current, Kelvin for temperature, candela for luminous intensity, and mole for amount of substance. So here we look into the different tables of SI units. So for length, we have the name, we have meter, the symbol is small m. The expression in terms of other SI unit is 1, and it is expressed in 1 base unit of SI. Similarly, we have mass, we have kilogram for mass, we have seconds for time, we have ampere for electric current, which is expressed in terms of C by S, which is ampere per second. In temperature, we have Kelvin. We have, for luminous intensity, we have candela, which is 1 CD is the SI base unit. Then we have mole. Then frequency we have, which is measured in terms of hertz, which is per second. So for example, rotations per second. So that is an example of frequency. Then force is measured in Newton, which is kilogram meter per second square. So that is one of the definitions in SI unit of force. Then we have pressure. So pressure is measured in terms of Pascal, and it is defined as a Newton per meter square. So remember that all of the derived quantities should have the basic fundamental quantity of the 7 units in the SI system. So for pressure, we have Pascal, which is Newton per meter square. So again, it is measured by kilogram per meter per second square. So this is derived. So if you go for Newton, it is kilogram meter per second square, and then you divide by meter square. So you get the expressed base unit, which is in the last column. Then we have energy, which is measured in terms of joules, and which is Newton meter, and it is expressed in terms of kilogram meter square per second square of SI base units. Then we have power, which is in watts. So it is measured in joules per second. Again, it is derived based on the fundamental SI units. Then we have electric charge, which is based on ampere second. So this is again derived in based of ampere and second in terms of SI base units. So next, so this covers the 22 components of the SI system based on the 7 fundamental aspects. So next, we have the electric potential, which is the volt, which is watt per ampere. So in terms of SI base units, it is measured as kilogram meter square per second cube per ampere. Then we have capacitance, which is in farad, and it is expressed in terms of you have C is this thing, electric charge per volt. So which is again per kilogram per meter square, fourth power of second, and then ampere square. Then we have electrical resistance, which is in ohm, so which is measured as volt per ampere. Similarly, electrical conductance is the inverse of electrical resistance, which is measured in Siemens. Then we have magnetic flux Weber, which is volt into seconds. So you need not memorize this, but you need to keep these in consideration. For example, all of these will be considered in different chapters of, say, electricity, thermodynamics, and various other subjects of engineering. So here we have magnetic flux density, which is measured in terms of Tesla. We have inductance, which is measured in terms of Henry. We have luminous flux, which is measured in terms of lumen. And we have illuminance, which is measured in terms of lux. And we have radioactivity, which is measured in terms of becquerel. We have plane angle, which is measured in terms of radian. We have solid angle, which is measured in terms of steradian. So these are the 22, if you look into, these are the 22 derived units with special names and symbols, which are used across different branches of engineering. So this is the expressed in terms of SI base units. So just to, you should be aware like how these are derived and what are the 7 fundamental units. So that is the key learning over here. So next we demonstrate the ability to use SI units in practical context. So here let's consider a scenario where we need to calculate the energy consumption of a household applications, for example, refrigerator. So how do we do it? So the example is, suppose you have a refrigerator at home and you want to calculate its energy consumption over a specific period. So the power rating is given as 150 watts. So what do you interpret by it? How do you calculate how much units it's going to consume? So based on that, you can find out how much you're going to pay for the electrical consumption. So we look at to the different steps of calculation. So step 1 is identify the given information. Then you convert time into SI units. Then you calculate the energy consumption. And finally, you convert energy into much more familiar units. So these are the different steps which you will use for calculating the energy consumption in a much more familiar units. So step 1. So power rating of the refrigerator P is equal to 150 watts and time of operation is 1 day is equal to 24 hours. So how do you go about calculating it? So let's go to step 2. As the time is given in hours, we need to convert it into seconds, which is the fundamental SI unit. So 1 day is equal to 24 hours, which is equal to 86,400 seconds. So that is how you convert. Then we have step 3, which is energy is equal to power into time. So using SI units, energy is equal to 150 watts into 86,400 seconds. So here you calculate it is almost 12.96 million joules. So, but joules is not a much more commonly used word for general interpretation. So next we look into how do we convert it into a much more familiar option. So joules is not a very intuitive for daily energy consumption. So let's convert it into kilowatt hours, which is a common unit. So 1 joule is 1 watt second, and 1 kilowatt hour is equal to 1000 watts into 3600 seconds. So energy is 12.96 million joules divided by 1000 into 3600. Your energy is 0.36 kilowatt hours rounded to 2 decimal places. So this is how you calculate the consumption of your refrigerator per day. So your refrigerator consumes approximately 0.36 kilowatt hours energy per day. So that way what you can do is then you can multiply your per unit charge, which means how much are you being charged, like how many pounds you're being charged per kilowatt of energy, and then you will get to know what is your electricity bill per day just because of this refrigerator. Similarly, the same is applicable for other units as well. So here I have listed a small task for you. So suppose Jack has a car with a mass of 1,000 kilograms traveling at speed of 20 meters per second. Then you need to calculate the kinetic energy of the car. So kinetic energy. So I'll give you a hint. You will have to use the kinetic energy formula, and then you have to convert the all of these given data into the basic standard format of metrics of the SI unit. Another example is, suppose there is a swimming pool of depth of 3 meters and find the pressure at the bottom of the pool due to the weight of the water above it, given that density of water is 1,000 kilogram per meter cube and acceleration due to gravity on earth is 9.81 meter per second square. So probably you can give it a try, and then you can let me know like what is your interpretation. You are free to use Google or books and all to carry out this calculation. So I think today's session was a short one just to begin with. So in case if you have any questions, you can let me know.
For that last question, I don't understand. Do I use the same formula for kinetic energy?
Kinetic energy, it has a different formula. So what I will do in your mail, I will just send you the formula for both of these, and then probably you can use it to calculate yourself.
Yeah. So then the bottom question, which formula would I use for that?
The bottom question will have a different formula for calculating the pressure. So it will use Pascal. So pressure at the bottom of the pool. So for that also, I will send you the formula. So probably you can use that to calculate the pressure at the bottom of the pool. So I will separately email you. So that will be much more clear to you.
Yeah.
Okay. So in general, also I'm saying like in case if you have any questions, I will just write you a hello email, and you can reach out to me at any point of time with your queries. If you need any text, if you need any books, or if you need any other help or videos or any other resources, I'll be glad to help you at any point of time. So
Yeah.
today's session, I purposefully kept it short just to give an introduction to engineering, and just slowly by slowly we can get into it so that you can understand the basic concepts.
Yeah.
So today's concepts was basically related to the SI units and how it is used. So that portion, I hope it is somewhat clear for you. So I guess like that's all for today. So we'll be joining in for next week for the second session. Meanwhile, I will write you an email for these two formulas. And I think you have other sessions tomorrow, right? Tomorrow, day after tomorrow as well, right? So in any case, you can either write to me or you can write to Raman. So whatever help you need, we will be there to help you out.
Thank you.
Thank you. Have a great day. Thanks a
You
lot.
too.